The Aharonov-Bohm effect is a fascinating phenomenon in quantum mechanics that challenges our classical understanding of electromagnetic forces. In classical physics, particles are influenced by electromagnetic fields, electric and magnetic fields. So one might expect that if these fields are zero, there should be no effect on a charged particle. However, the Aharonov-Bohm effect shows that even in regions where the fields are absent, particles can still be affected if the electromagnetic potentials are non-zero. How does this happen? In quantum mechanics, particles like electrons are described by a wave function, which carries both amplitude and phase. The electromagnetic potentials, although not directly observable in classical mechanics, influence the phase of the electron's wave function. For example, consider electrons traveling in two different paths around a region with a confined magnetic field, such as inside a long, thin solenoid. Even though the electrons never pass through the magnetic field itself, the vector potential associated with the field alters the phase of their wave functions. When the electrons meet again, the phase difference can cause interference patterns that differ from what would be expected if the potentials were absent. In this way, the electrons feel the presence of the magnetic field indirectly. Could this phase shift be significant? Yes! The interference pattern observed in experiments is a direct measure of the phase difference caused by the electromagnetic potential. This finding was surprising because it indicates that potentials are more fundamental in quantum mechanics than the fields themselves, a notion that defies our classical intuitions. A common question that arises is, how can something that we can't directly observe, the potential, affect a measurable outcome like interference? The answer lies in the principle of gauge invariance in quantum theory. While the absolute values of the potentials are not observable, their differences are, and these differences lead to measurable shifts in the wave function phase. Experimental setups like the famous double-slit experiment modified to include a solenoid have repeatedly confirmed these theoretical predictions. Another example involves the electric Aharonov-Bohm effect, where charged particles moving in regions with zero electric field can still experience phase shifts due to time-varying electric potentials. This further reinforces the idea that in quantum mechanics, the potentials, not just the fields, play a crucial role in determining the behavior of particles. In summary, the Aharonov-Bohm effect demonstrates that particles can be influenced by electromagnetic potentials even when the corresponding fields are zero. By altering the phase of a particle's wave function, these potentials lead to observable interference patterns, challenging the classical view of forces and highlighting the subtle, non-localic nature of quantum mechanics. How does this change our understanding of the fundamental forces in nature? It reveals that our most basic interactions may operate on principles that extend beyond direct observable fields, urging us to rethink the foundations of physics. The Aharonov-Bohm effect demonstrates that quantum particles such as electrons can be influenced by electromagnetic potentials even when they travel through regions where electric and magnetic fields are absent. This contradicts classical physics, where forces only arise from direct field interactions. Instead, in quantum mechanics, the vector potential itself plays a fundamental role in determining the phase of a wave function. This phenomenon suggests that potentials are not just mathematical tools, but have real physical significance. For example, electrons passing through a region with no magnetic field can still exhibit a phase shift due to the presence of a vector potential, altering their interference pattern in a double-slit experiment. It's like walking on an invisible treadmill. The floor appears flat, but something unseen is affecting your movement, subtly changing your final position. In classical electromagnetism, the electric and magnetic fields are the fundamental physical quantities that determine particle motion. However, in quantum mechanics, the electromagnetic potential influences the phase of an electron's wave function even in field-free regions. This implies that electromagnetic potentials are more than just convenient mathematical constructs. They possess real physical effects. The Aharonov-Bohm effect challenges the classical assumption that only forces derived from fields can affect charged particles. For example, in superconducting circuits, vector potentials influence electron flow without direct electromagnetic field interactions, leading to measurable shifts in quantum states. It's like feeling the presence of an ocean's current without directly seeing the waves. Something unseen is affecting movement in a measurable way. The Aharonov-Bohm effect is typically demonstrated using a two-slit electron interference experiment where a solenoid, a coil of wire generating a magnetic field, is placed between the slits. The electrons pass through regions where the magnetic field is zero, but their wave function still acquires a phase shift due to the magnetic vector potential. This phase shift leads to a measurable change in the interference pattern on a detection screen, confirming that quantum phase changes can occur without classical force interactions. For example, physicists have observed the AB effect using electron microscopes to measure shifts in electron interference patterns around magnetized materials. It's like the smell of food affecting your appetite. Even though you haven't touched or tasted it, the influence is real despite no direct physical interaction. Gauge theory describes how fundamental forces in physics arise from symmetries in nature, and the Aharonov-Bohm effect is an example of a gauge invariant phenomenon. In quantum mechanics, the phase of a particle's wave function can shift under a change in the electromagnetic potential, even if the fields themselves are absent. This shift is measurable and alters observable interference patterns, reinforcing the importance of potentials in modern physics. The effect highlights the deep connection between gauge fields and quantum behavior. For example, in quantum field theory, the AB effect has implications for understanding electromagnetic interactions in superconductors and condensed matter physics. It's like adjusting a thermostat in a room. You may not see the temperature change immediately, but the effect gradually influences everything inside. The Aharonov-Bohm effect suggests that quantum mechanics operates on principles beyond classical local interactions, hinting at a form of non-locality. Particles respond to the presence of an electromagnetic potential even when they are spatially separated from the source of the field, which challenges the classical idea that objects must be in direct contact with a force to be affected by it. Instead, quantum mechanics allows influences to arise from field-free potential. For example, similar non-local effects appear in quantum entanglement, where measurements on one particle instantly affect its entangled partner, regardless of distance. It's like feeling a change in pressure before a storm arrives. The atmosphere is preparing for a shift, even before the wind or rain begins. The AB effect is closely related to topological phases of matter, where systems exhibit global properties that remain unchanged under small perturbations. In topological materials, electrons experience phase shifts due to electromagnetic potentials, leading to exotic behaviors such as quantized resistance. These effects are fundamental in developing quantum technologies like topological qubits for quantum computing, and the presence of the AB phase shift underscores the deep link between geometry, topology, and quantum mechanics. For example, the quantum Hall effect, which is used in precision electrical resistance measurements, relies on similar topological properties. It's like tying a knot in a rope. The shape remains even if you twist or stretch the rope slightly. The topology dictates the outcome. The AB effect is not just a theoretical curiosity. It has practical applications in fields such as nanotechnology and quantum computing. It helps scientists design devices that manipulate electron phases for advanced quantum electronics. And in mesoscopic physics, where electronic properties of small-scale materials are studied, the effect is used to control electronic interference patterns. Understanding the AB effect provides a foundation for engineering future quantum-based technologies. For example, nanodevices use AB interference to enhance precision in sensors that detect minute magnetic fields. It's like designing a high-precision clock. Small phase adjustments can lead to significantly improved accuracy in timekeeping. Despite being experimentally verified, the AB effect remains conceptually challenging because it implies that potentials alone, without force fields, can influence particles. This raises fundamental questions about the nature of reality in quantum mechanics and whether our classical understanding of forces needs revision. Some interpretations suggest that the vector potential is more than a mathematical tool, it may have direct physical significance. Resolving these conceptual puzzles continues to be a topic of debate among physicists. For example, some researchers propose alternative interpretations of quantum mechanics where the AB effect could be explained differently. But standard quantum theory remains the most widely accepted explanation. It's like finding a new force of nature that affects objects without touching them. Challenging but intriguing to explain within existing theories. Future research into the Aharonov-Bohm effect focuses on exploring its implications for quantum field theory, quantum gravity, and fundamental physics, with scientists investigating whether similar phase shift effects occur in other force fields such as gravitational potential. New experiments aim to test the AB effect in even more controlled environments to refine our understanding of gauge theories, and these studies could lead to deeper insights into the nature of space-time and quantum interactions. For example, physicists are working on gravitational analogs of the AB effect to see if similar principles apply to curved space. It's like discovering that invisible wind currents can change the course of an airplane. Even though you can't see the force directly, its effects are undeniable.